In this video, we're going to be covering linear models. So first, let's get our learning targets into our notes. And we're going to be able to describe the rate of change in y-intercept, right? So this is your slope, right? Constant rate of change for a linear model. In everyday language, right? It's about interpretation. And then we're going to be able to draw a linear model that fits the data well and use that, right? We're going to use this model. First, we're going to draw one, then we're going to use it to make an estimate, right? We're going to be talking about making predictions, right? This is the bold and big stuff, right? So another challenging lesson, but I think we can muster our way through it. Let's go. Okay, so as we get started, we're going to start with a what do you notice, what do you wonder with respect to crowd noise. So on our x-axis, we see the numbers 60 through 80. And this is representing the number of people in thousands. So 60 is equivalent to 60,000 people. And on the y-axis, the maximum noise level in decibels. So one of the things I notice is that as the number of people increases, the noise level goes up. So they have it as more fans generally means more noise. So I guess crowd, we're referring to a crowd base of fans. What else do we notice? Well, let's take a look at like a specific value, right? So somewhere around like 65,000 fans looks to me like there's several different decibel levels there. There's a little around 115, and then there's another one there. So it seems like at 65,000 fans, there's more than one decibel level. So maybe they had 65,000 fans in one location and measured it, 65,000 fans in another location and measured it, and they were more excited at some point. Or maybe it's a measurement in various times in a concert where there's 65,000 people, something like that. So at 65,000 fans, there are 3 different noise levels. And again, they're referring to these 3 right there. What else is going on here? I see this blue line, right? So I see this blue line right here. That looks to be a linear model, right? Trying to approximate all these actual values. And it looks like if you continue this line, it's going to go through right there. And now the problem with that, for me, is that that's at 105, and I noticed that the y-intercept is at 22.7. But really, if you look at the x-axis here, this isn't at x equals 0. So x equals 0 is like way over here. So really, the vertical axis is like that. So I'm just saying that we're a far cry from 0. And if we're going down by 5s on the vertical axis, then this isn't 5 away from 0. That 0 is way down there. So I guess the question is, where's the origin? In modeling, it's not uncommon to sort of break the scale. I believe that they should have a line right here that shows that this scale has been broken to accommodate the graph, because really the focus is the data right there. Okay. The other thing I noticed is that the slope is 1.5. So that means we have our change in rise or change in rise or change in run, right? That's our slope. And so for each additional x value, but remember that's 1,000. So for every additional 1,000 people, because this is 1.5 over 1 technically, that's my slope or my rate of change. For each additional x value, we're going to get an additional 1.5 increase in decibels. So as we move this way, we go up that way. And that rate of change is 1.5. When we have nobody in attendance, then the decibel rating is at 22.7, or maybe that's sort of like the ambient noise in the area, right? It's not dead quiet. So that's the real life interpretation of that model. Complicated. I guess the last question is, how come all the points aren't on the line? Right? Why aren't these all on the line? Well, that's because life is not perfectly linear. Never is, really. Things just are approximately linear at best. So it makes sense to me that the more people that are there, the louder this place gets, but not on a perfect linear scale. We can still build a relatively accurate model around that. So this next stage of the game, what you're going to have to do is you're going to use the link to watch the video. The link is entitled Oranges in a Box, and it's just a very short, silent video to where you're going to notice that there are 3 oranges in a box, and then you're going to record the weight. Then they put another orange in, you're going to record the weight. Another orange, record the weight. And I think it's really oranges and clementines, if I'm not mistaken. If you'll notice, you have to let me know what you think about that one. But anyway, you're going to go ahead and record all 10 of those weights. Then you're going to go to Desmos, right? You're going to go to Desmos, and you're going to use these values to build a table in Desmos. Desmos will then create a graph for you, and you're going to copy that graph over to here. Once you've copied the graph onto your paper, you're also going to copy the line from Desmos that fits the data well, right? It's not going to fit it perfectly, but it's going to fit it well. Now, so after you've recorded, right? First, record the data. Once you have the data all set, you're going to go into Desmos, and you're going to come over to this top left-hand side, and you're going to hit plus, because we're not entering in a function, we're entering in a table. And you're going to select table. Also, you want to go over to this settings, and you want to set your X values to be greater than -1 and less than 10, or right, these are, I think, less than or equal to's. Either 10 or 11, right? You want to be able to have all 10 of your X values here. And then for your Y values, you're going to be less than or equal to 4 and greater than or equal to -1. And the scale, or I forget what it says, something like a count, is going to be step, actually, is what they call it. The step for the Y's is going to be at 0.5, and the step for the X is going to be at 1. Meaning the scale is going to count by 1 here, and the scale over here is 0.5. And that's just to match your handout. So get these settings squared away by hitting this wrench. Get this option for a table, and then let's move on. Once you get into the table, you're going to enter in your values. So just for the record, the first value here is 1.027. The next one should be 1.162, so on and so forth. And you're going to have all these values. And what's going to happen over here on the graph is these dots are going to start to fill in, right? And you're going to get something that looks like that. It's going to be a positive motion. Then once you're done entering all 10 dots, I want you to come into this second line and type in Y. Then type the number 1, and it's going to put a little subscript. And then you're going to find the tilde. That's going to be one of the keys on the board. So you're going to do that little tilde. And then you're going to write M. And you're going to have to choose the letter. Right? You're going to have to go back and forth on the keyboard between letters and numbers. M, then X, and the number 1, and it'll make it subscript again, plus the letter B. Right? So Y is in the numerical section. 1 is in the numerical section. X is in the numerical section, and 1 is in the numerical section. Plus is in the numerical section. The ABCs, as you'll see it, that's where you have to go to get this, this, and this. All right? Everything else is numerical. So black is in the ABC keyboard, red is in the numerical. Once you type all that in, you're going to get a whole bunch of cool stuff. So press pause, right? Press pause and do the work. Gathering this information on your own is important. You will need to know, right? You'll need to know this for an assessment on entering data into a table and then sketching that scatter plot. So make sure that you don't just copy things from me. All right, do this on your own. Press pause and complete all of the data gathering and all of the entering and draw your picture and then check back in against my work. If this is too much on your own, feel free to reach out to your Algebra 1 teacher for some advice and help. When you're done, you should have a picture that looks like this, a table of values that looks like this, and then you have this information. After you enter this equation into Desmos, it pops out a bunch of information. So don't sweat anything like this. And by the way, if you needed help, I've also provided a link for making a table of values. So that link was also provided on the homework piece if my walking you through it verbally doesn't work. Nice quick short video of somebody else showing you how to do that. But anyway, here's the main piece we wanted to grab. M is always has been our slope, and B always has been our y-intercept. So it looks like weight, right, because that was our y value, y is equal to mx plus b. Weight is equal to, my slope is 0.2158, so let's just call that 0.216, because the 8's bigger than a 5, so we're going to round that up. And then 0.345, because the 1's smaller than a 5, we're going to leave that alone, so 0.216, and the x value is the number of oranges, so times, I don't know, number of oranges plus 0.345. And so this must have been the weight of the box before we put any oranges in it, or at least that's our estimation of that piece, right? We don't actually know because we started with 3 oranges in the box, so we don't know exactly what the empty box weighs. But every time we put an orange in, on average, we're going to gain 2/10 of a, I guess it was a gram. I didn't catch the units on it. I just went and peeked. It's kilograms. Yeah, I was way off there. Kilograms. Okay, so for each additional orange, looks like our weight goes up by about 2/10 of a kilogram. And 3/10 of a kilogram was about what the box weighed. Okay, so let's go answer their questions. So let's proceed with answering some questions. So we know that this is our slope. We know that this is our y-intercept. So for slope, let's agree to use 0.216. And for our y-intercept, let's agree to use 0.345. Now remember, this is the weight in kilograms. And then it says to estimate the value of the slope. So let's come down here. So 0.216 is the estimated value of the slope. And so what that stands for, right, is the approximate weight of each orange added to the box, essentially, right? Because the weight goes up, right? We're going to have 0.216 kilograms per orange. So this is over 1. So the orange corresponds to the 1. The weight corresponds to the 216. So essentially, 0.216 kilograms per orange, or 0.216 kilograms per orange. Okay, and now we have estimate the weight of a box containing 11 oranges. So again, we have our weight is kilograms, 0.216 times the number of oranges plus 0.345. So all we do is plug the number of oranges into our function and then evaluate. So they said, well, hey, how about when this is 11? What does the weight become? So no problem. We process 0.216 times 11, add 345, and we get a value of 2.721. And so we've recorded our answer here, right? So about 2.721 kilograms, which at 10, it was 2.569. So it went up by about 216 kilograms. All right. How about 50 oranges? Okay, well, let's take a pause. Now, 50 is pretty far out on the line there. We can estimate a value for that, but I don't know how accurate it's going to be, but let's go ahead and let's trace out the number 50. So we're going to put 216 times 50, add 0.345, and we're going to get 11.145 kilograms. So 11.145 kilograms. Will this estimate be close to the actual value? Well, I think it'll probably be pretty close to the actual value because all of the other values are pretty clustered. So assuming most of the oranges are, there's some variability in sizes of orange, but, we'll see how it goes. I think the further away you get from the data that you have, right, 50 is way larger than 10, right? So 11, I'm okay with this estimate. This one, I don't know. It's a little far from what we collected. If we had collected maybe 30, 40 oranges in the data that goes with that, maybe I might guess the 50, but the further away we get from our data set, the more untrustworthy our estimate becomes. But we can still create that estimate, which is, again, why we keep reinventing coronavirus models so many times, right? Because we keep adding more data to the pile so we can get a more accurate estimate. Now, this next question says, estimate the coordinates of the vertical intercept, but we know the vertical intercept. What might this represent? We've already discussed this. The vertical intercept right here, this is that said vertical intercept, right? And what that represents is the box with no oranges, right? It's just the empty box, right? We'll say empty box. Okay, and really, empty. I was just trying to be funny. Now this last two questions here, it says, which points are best fit by your linear model? How do you decide? And which points are least well fit by your linear model, and how do you describe? So let's take a look at the model. First, let's deal with the good fit, right? So we'll do the good fit in blue. So best fit, I would say for 6 oranges, that was pretty good. That landed almost right on the model. And 3 oranges landed right almost on the model. And then the 8 oranges, How about least well? So in red, sort of, the bad color, right? Definitely 7 oranges. Looks like the line overshot the mark a little bit. And then at 4 and 9 oranges, looks like also that happened. At 5, we undershot the weight a little bit. And at 10, we undershot the weight a little bit. So it's really about, how close did the points come to the model, or how close did the model come to the actual values. So this model is actually really good. And just to double back, not that you need to know this, but that R squared value, the closer that is to 1, the better the model is. So seeing that it was 0.985 or 0.99, this model is actually like really good. And to be perfectly honest, in the statistician's world, pretty much most of those points were really, really well fit. But if you're looking at just these points and comparing them, some of them were a little bit closer fit than the others. That's it. Just as an outgoing question, what happens if the box was heavier itself? What would happen to the steepness of the line, right? We're still just adding the same oranges. It would still be the same steepness, but it would be at a higher initial value. So the line would be probably just higher like that. That's all. Food for thought. So next we have now we're going to discuss, right? The scatter plot down here has the ingredient cost and the X value. The scatter plot shows several food items, price that they're selling, and why is the Y cost of the ingredients. So a actual value would be like this value right here. That item cost $1.50 to make and about $5.25 to sell. Right, so a little bit of a markup in the food industry versus, like, say, Nike shoes, like 300 to 500% markup on shoes, right? So when you pay $120 for those Nike shoes that you think are so special, they're not. They're just total garbage, made in a third world country, and they're just marketed, right? And they're marketed to feel like they're a superior shoe than a lower price shoe. They're not. You're just paying for a bunch of marketing, and you're paying for the markup. Take a business course. You'll learn about that one. All right, let's move on. So let's take a look now at the model. Right, we have a model here that says, looks like if you had no ingredients, it's going to costs about 76 cents to make, meaning that there's just some overhead just to turn on the lights, right? So that's what that's all about. And then I guess for every increase in one ingredient dollar, you're going to expect $3.48 of the price to go up. Okay. So what is the predicted sale price of an ingredient that has $1.50? So when you hear the word predicted, that means we're going to go to the blue line. Okay, so let's use a blue pen to signify that specialty. So we'll follow the $1.50 up to the blue line, and then we'll come over, and it looks like that's about $6. Okay, next. What is the predicted, right? The predicted ingredient cost of an item is a sale price of 7. So we'll start off at 7, follow it over to the line, follow that down, and I would say that that's probably around $1.75. Okay, next. What is the slope of the linear model? Again, the linear model is 348, right? So 348. Technically, that's going to be dollars in sale price for every increase in ingredient cost. Right, so it's really dollars per dollar. So it's $3.48 goes up every time you add $1 on the ingredient costs. So add one, if you go from $1 to $2 in ingredient costs, you're going to go up $3.48 in sales cost. And then finally, it says, what does the y-intercept mean? The y-intercept of the linear model, right? What does it mean in this situation? Again, I've kind of already said that's sort of the base cost, right? 0.76 or 76 cents is the sales price when there is $0 in ingredient cost. And the question is, well, what does that mean in this situation? Does it make sense? So first off, if there is $0 in ingredient cost, we're going to recommend 76 sales price. Does that make sense? No. But the point of it is we're saying there must be some sort of cost to rent the building, and you're going to have all this stuff going on. And if you distribute it across all items, it comes out to be about 76 cents per item. So that's the bottom line, is there is a sort of a base cost. You got to turn on the electric, you got to turn on the heat, maybe some internet, turn on the credit card machine, all this stuff. That's all your sort of fixed costs. And that also gets applied to all of your products. Okay, for the next couple of questions, we're going to keep going back and forth between question A, using the horizontal axis as X and the vertical axis as Y. We're going to interpret the slope of these scatter plots. And then for B, if the relationship holds true, we're sort of going to follow this down to a y-intercept and try to interpret, right? Interpret what the y-intercept of each model represents. So first, let's start with model A. On model A, it appears that we have age in years and reaction time, and it looks like it's going down. So I guess what we're saying is as we increase in years, reaction time gets lower. And to be very specific, it looks like that decrease is 9.25. And I say decrease because it's negative. So for every increase in age of 1 year, right, as we go up in age by 1 year, the linear model estimates that the reaction time decreases by 9.25 milliseconds. Now let's take a look at the y-intercept for this, right? If we were to back it up on the y-intercept, right, it looks like we're going to go to 400. So how do we interpret that? The reaction time estimated by the linear model for a newborn is 400 milliseconds, right? So there's our 400 milliseconds. And why do we say newborn? Because age in years. The y-intercept is the value when x is 0. So how old are you if you're 0? You're a newborn, right? And the reaction time that's estimated, because these are estimations, right? So going back to the part A, the linear model estimates reaction time decreases by 9.25. Doesn't guarantee. It's just built on the data that we have. And now the funny thing is that the data we have only goes to like 23 years old and starts at 10 years old. So really, when you start guessing outside of those years, this model may not predict well. Maybe we get sort of, as and the reaction time's decreasing. I think that means that we're getting faster. probably bottoms out, and then we go back to being longer, right? Sort of, we go out of this world the same way we came in, slow. So next, we move on to our model over here where we have a positive slope of 0.44 and a positive y-intercept of 0.04. Looks like we got number of bananas, price in dollars. So I guess that for every banana, we're going to increase 44 cents, right? And the price of no bananas is 4 cents. Okay, so there you have it. For every additional banana, the linear model estimates that the price increased by about 44 cents. And then the price estimated by the linear model for purchasing 0 bananas is 4 cents. So again, there's this sort of like cost associated with walking into the building, right? But I think if you walked into the store and you bought no bananas and you walked back out, no one's going to say, hey, 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 you owe us 4 cents. Next, we have room size in square feet, and then the cost to install flooring. So of course, the bigger the room, the more it costs to floor it. And here's our model, the blue line, with a slope of 4 and a y-intercept of 87. So again, to interpret that slope, for each additional square foot, the cost is going to go up by $4. And I guess the room size of 0 square feet has $87 cost associated with flooring it. Again, what? So the bottom line is you probably can't get out of flooring any room without at least spending $87. Or maybe that's the equipment cost to get into it. Maybe the knife and the tools associated with cutting and all that stuff cost about $87, and then from there on you get $4 of square foot cost of material. So go ahead and grab the officials and put that into your notes. You may need to press pause. Okay, and our last model is temperature in degrees Celsius and volume in cubic meters. So it looks like as the temperature increases, the volume decreases. So for each additional increase in Celsius degree, or each degree increase in Celsius, you're going to have a volume decrease in cubic centimeters of negative 2.4, or for each increase in Celsius degree, the volume goes down by 2.4 cubic centimeters. And then 25 degrees, I guess that means a temperature of 0 would have a volume of 25 cubic centimeters, or at freezing, because remember, Celsius works so much better than the American Standard Fahrenheit version, right? Celsius at 0 is freezing, and at 100 is boiling, as opposed to 32 degrees is freezing in Fahrenheit and 212 is boiling. That makes a lot of sense. Not. So to wrap this up, I guess the big deal here is that while working in math class, it can be easy to forget that reality is somewhat messy, right? Not everything, right? Not oranges weigh exactly the same amount. Beans have different lengths, and even some persons running a race multiple times will have different finish times. Like a certain person may finish a race, right? Life is messy, right? And so predicting and estimating additional results, as long as we continue to keep in mind that reality will vary a little bit from our mathematical models. Okay, so the data in the scatter plot that I'm about to show you represents the price of a package of broccoli and its weight, right? And it can be modeled in this sense. So the data doesn't fall in the line because there's other factors that go than weight that go into the price, such as the quality of the broccoli, the region where it's sold, yada, yada, yada. So let's take a look. Again, here's our model, right? So if we look at the y-intercept, right? A zero weight, right? No broccoli costs 92 cents. Packaging, I guess, right? Preparing the package, shipping the package, and all that stuff, getting it to the store. Then it appears that for each additional weight in pounds, the price of broccoli goes up by 0.46. But I wouldn't say 0.46. I'd say for each additional pound, I guess broccoli costs about 46 cents a pound. Ta-da! And then there's lots of other stuff. Feel free to read on your own. That's all I got for you. Take care.